Welcome everyone. For today's prep, we're going to start looking at partial fractions. So a little bit different than kind of a change of pace. We've been dealing with trig functions. Now we're going to be dealing with rational functions. So where we have a polynomial divided by another polynomial. And the idea behind partial fractions is, well, a lot of times we have fractions and we're adding or subtracting them. The goal is get a common denominator, combine them, get them into one single fraction. It's kind of what we're used to. So we're used to getting, if we have two separate fractions, we're used to getting a common denominator so that we can combine them into a single fraction. What we're going to be doing with partial fractions is kind of the opposite, kind of reverses it. So common denominator goes one way, partial fractions goes the other way, this idea. So what partial fractions is going to do is it's going to take one single fraction like this, it's going to break it apart. Now why would we want to do this? Well, when we break it apart, each of these individual fractions are ultimately going to be easier to integrate. So something like this, complicated, but individual fractions like this, easier. All right, so the idea is how we're going to do our partial fraction decomposition. And this looks like a lot. We'll come back and talk about this more and more. But the idea is we factor our denominator. So we want to factor, we're looking at the factors in our denominator. And we're going to classify them in a few different ways. So the most common that we'll see are these linear terms. So if we factor our denominator, a lot of times we're going to end up with just something like ax plus b. So for each linear term that we get in our denominator, there's going to be a kind of a partial fraction that goes with it. So if we see this as a factor in our denominator, ax plus b, well, that's going to give us capital A over ax plus b in our partial fraction decomposition. All right, so we'll be talking about these other ones later on. Let's look at an example though where we have a linear term. So we're just going to look at that example that we had right on the first page there. So this function 2x plus 5 over x minus 1 times 3x plus 4. And we're just going to write out the partial fraction decomposition. We're not going to figure out the numerical coefficients just yet. So we're just going to see how this works. All right, so we look at our denominator, and it's already factored for us, so that's nice. And we see that we have two linear terms. So two, we'll say distinct. They're different. We've got two distinct linear terms here. All right, so each of these distinct linear terms, when we do our decomposition, when we break it apart, is going to get its own fraction. So first, the x minus 1 will get its own fraction. And then second, the 3x plus 4 is going to get its own fraction. And we call A and we call B here the coefficients. So these are numerical numbers. These are constants that we ultimately will have to figure out. And we'll see how to do that in a few seconds. But this is just the general partial fraction decomposition for this function. Now, if you wanted to, if you wanted to be, you could say A1 and A2, but can make mistakes with that. But that sometimes helps if you have a lot of linear terms or a lot of kind of repeated linear terms, as we'll see. But when you only have like two, you could just probably go in alphabetical order. A, B, C, D, E works. All right, so let's actually see now how to figure out A and B. And I have a summary here for how to find the coefficients. And there's a few different strategies. One of them is, and this works best with our linear terms, the idea is just to plug in different x values and see what you get. Another strategy is to compare coefficients. So we'll be trying these out. And let's start with this example. So we're going to actually prove this decomposition. All right, so our first step is, when we're doing a partial fraction, is just to write out the decomposition. Which we already did for this one. So our decomposition is going to be the 2x plus 5 over x minus 1 times 3x plus 4. And we said that that was equal to a over x minus 1 plus b over 3x plus 4. So each of those separate linear terms got its own fraction. All right, so we write out the decomposition. Then we multiply both sides by the common denominator. So that's the next step. So we're going to do that. So we're going to multiply everything on the left here by that common denominator, x minus 1 times 3x plus 4. And then we'll multiply everything over here by that same x minus 3 times, or x minus 1 times 3x plus 4. All right, so why are we doing this? Well, it's going to get rid of the fractions for us and make it easier to solve for the coefficients for those a and b terms. All right, so on the left, the denominators just cancel. So we're left with just the 2x plus 5. And on the right, when we do this, when we distribute the x minus 1 times 3x plus 4 into the parentheses, when we take it to the first fraction, the x minus 1s are going to cancel. So that's just going to leave us with a times the 3x plus 4. So kind of like the opposite term there. And when we distribute this to our b fraction, well, in that case, the 3x plus 4s are going to cancel, and it'll just be the b times x minus 1. So we get this simplified equation to work with. And this is the equation we're going to kind of plug in different x values. All right, so let's start off with an easy x value. So you look at the two linear factors, and you figure out what x value would make the linear factor 0. So let's start with the easy one, this x minus 1. Well, the x value that would make that 0 is x equals 1. All right, so let's plug x equals 1 into this equation, and we're going to see what we get. So when we do this, plug 1 into the left side, we're going to get 2 plus 5, which is 7. And then if we plug 1 into the right side, we're going to get a. We don't know what a is yet. And when we plug 1 into here, we get 3 plus 4, which is 7. And then when we plug 1 into here, we don't know what b is, but then we get 1 minus 1, which is just 0. So we end up with b times 0. And this is an equation that we can solve for a. So if we do that, technically we don't even really need to write this b times 0. So to solve this equation for a, we can divide both sides by 7. And when we do that, we get a is equal to 1. All right. So we've got one of them. So now we want to find the other one. And, well, we dealt with this first, or the x minus 1 linear term. So now we could do the same thing with this second linear term, this 3x plus 4. We could figure out which x value makes this one 0. Now, we're going to have a fraction here if we try to solve this equation. So another option is you don't necessarily have to use the 0. You could pick some other x value. Make it easy to evaluate. So one that always is nice, just pick x equals 0. Easy to evaluate. So if we plug it in on the left side, we get 2 times 0 plus 5, so we just get 5. If we plug 0 in to the a term, we get a times 4. And then if we plug 0 into our b term here, well, we don't know what b is yet, but then we get 0 minus 1, so we get b times negative 1. And because we already know what a is, we can update our result here and then just solve it for b. So if we update, make our update, we get 5 is equal to 4 minus b. And if we solve that for b, we get b is equal to negative 1. And there we go. We've got our a coefficient, which we'll put into our first fraction there. And then we've got our b coefficient, which we'll put into our second fraction. So then the last step is just make sure you write out the actual decomposition. So we were proving this. Normally, we don't have this part. So normally, we just have the fraction, and then we're trying to get the decomposition. So once we've found the coefficients, we just want to make sure, update our formula. So in this case, our function 2x plus 5 over x minus 1 times 3x plus 4 is equal to the a value, which is 1, over x minus 1 plus negative 1 over 3x plus 4. So we're just filling in the a value, and we're filling in our b value there. And you just got to be careful. One easy thing to do, just make sure you're putting the a value on the right fraction, and you're putting the b value on the right fraction. All right, so let's try one more of these. And I want to look at the case where we end up with what's called an irreducible quadratic. So if we go back up to our big table here, so there's a few different options for what can happen. We can have a linear term like we saw that only happens once, only have one copy in our denominator. We can have a linear term that happens more than once, so we say has multiplicity n. Or we can have an irreducible quadratic. So this is a quadratic that you can't factor any further, and it only happens once. Or the other option is you have an irreducible quadratic with multiplicity more than 1. So if we have an irreducible quadratic, a quadratic that we can't factor down any further, the format for our decomposition is it gets its own fraction, and the format is ax plus b. All right, so let's look at this one. 4x cubed plus 5 over x squared times x squared plus 1. All right, so what do we have here? Well, we've got the x squared, and then we've got the x squared plus 1. So the x squared, this is actually a linear term that happens twice. It has multiplicity 2. So what do we do in that case? So if we have a linear term that happens more than just once, we make separate fractions, and we basically count up until we reach the multiplicity. So we start with our regular linear term partial fraction. Then we have the denominator squared. And then we keep doing this until we reach whatever the exponent is. So in our case, with with that x squared term, that's a linear term with multiplicity 2. So we'll have a fraction a over x. and then we'll have a second fraction, b over x squared. And so this linear factor here happened twice. So we're getting two fractions. And our denominator counts up until we get to that x squared, until the multiplicity matches. All right, so we're getting two fractions for that lone x squared term. And that's because this x squared is a linear term that happens twice. Now the difference, this x squared plus 1, this is an irreducible quadratic. So this can't be factored any further. So we can't factor that one any further. This x squared here, that one we could actually factor. You could think of that as x times x. So we got two fractions from that. But this x squared plus 1, that's an irreducible quadratic. We can't factor that one any further. So the format for the decomposition in that case is the denominator is going to be the x squared plus 1, and the numerator is going to be this form cx plus d. Or if it happened first, it would be ax plus b. So for an irreducible quadratic, this is the format that we get. So this example, what we have is we've got two things. We've got a linear term of multiplicity 2, and we've got an irreducible quadratic of multiplicity 1. So our irreducible quadratic was that x squared plus 1 term. Can't factor it any further. And the linear term of multiplicity 2, that was the x. So it gets two separate fractions there. All right, so we're going to be practicing more. See how to get the coefficients. So do the partial fraction decomposition, multiply everything out, and then see how to get these coefficients. So we'll be practicing this. So we'll see you then. Bye-bye.